Hello and welcome to my presentation. My name is Johannes Popp and I'm currently working as a PhD student at the Technical University of Munich. Today I will present a modeling approach of terahertz comp emission in different frequency quantum cascade lasers, and this work was done together or in collaboration with the CNR institution in Florence and the Central Research Laboratory of the Hamamatsu Photonics company in Japan. I will start with a small motivation. So, quantum cascade laser. What is a quantum cascade laser? It's a special type of semiconductor laser emitting in the mid-IR and terahertz regime, and is used for gas sensing applications. Commercially, you could use this one, or this is a main research topic. But here we can close the terahertz gap between photonics and electronics using such quantum cascade lasers. On the lower left-hand side, you can see a schematic of such a waveguide where we have a metal waveguide, and in between the active gain medium, which consists of a multiple quantum well heterostructure. This multiple quantum well heterostructure, so the conduction band profile, is given on the right-hand side, together with the probability distributions of the quantized electron states. And these states act as our laser levels, both in the terahertz as well as in the mid-infrared regime. So currently, direct terahertz QCL operation is only possible up to 250 Kelvin. So the record design was published in 2021. But actually what we want to do, or what we want to have, is a device for commercial applications where we don't need cryogenic or thermoelectric cooling. So what would be nice? Different frequency generation could help us. So we use the matured mid-IR QCL sources with dual wavelengths. So we have two frequencies in the mid-IR. We provide a gain medium with a large second-order nonlinear susceptibility, and so we can generate stable terahertz comp emission or terahertz operation at the first point at room temperature without the necessity of population inversion. Here, normally they use Cherenkov phase matching schemes because the terahertz absorption in the active gain medium is so high in comparison to the substrate that they want to couple out the light via the substrate. So coming back to the active gain medium and to the conduction band profile on the right hand side, we have our mid-IR quantum cascade laser, and it's described by one upper laser level and two lower laser levels, and the nonlinear mixing process or these transitions and the difference between these two frequencies gives us a third frequency in the terahertz spectrum. And the down conversion of electrons through optical transition is then followed by the extraction and injection into the next period. Here it is described by allophonon scattering. Now, I already said it, but we also want to have terahertz frequency comp emission. So we need a single mid-IR mode generated by a frequency detuned distributed feedback grating. This you can see here on the right-hand side. So here I have a schematic of the cross-section of such a waveguide with the high reflection coding on the left side, and on the right side the optical power is outcoupled. And here above the active region we have this indium gallium arsenide guide layer, and this one shows the grating we need to get this DFB single mode. at the frequency omega-1. Then we also want to have this Fabry-Perot frequency comp for the mixing, and so the generating of a broadband frequency terahertz comp. And here we have to detune the grating from the gain maximum, because otherwise our DFB grating would suppress this Fabry-Perot comp, and we would only see a single mode, so this DFB mode. So this is what the experimentalists do, and what we now want to do is we want to model this kind of devices with our multi-domain modeling approach. So our modeling approach consists of a charge carrier transport framework, the so-called Monaco framework, and the Generalized Maxwell-Bloch framework, which is the so-called mbsolve project. So we have the charge carrier transport. Here we use the Ensemble Monte Carlo simulation tool for carrier transport simulations, but also to extract scattering rates and dephasing rates, which we need as inputs for our Maxwell-Bloch simulations, and the Schrödinger-Poisson equation, which is necessary to calculate the wave function eigenenergies, which are needed for both EMC but also for the Maxwell-Bloch simulations. And then we have our mbsolve framework, where we have the Lindblad equations for the time evolution of our density matrix, so of our quantum system, and the Maxwell's equations for the optical field propagation in the cavity. The interaction is here described by the quantum mechanical polarization. Yes. So just saying a few words about our Monaco project, so about the object-oriented Matlab project. This one is a so-called quantum cascade device engineering tool. So we have an optimizer based on the Bayesian optimization. Then we have a module setup and a module backend to generate the input files and write the input files for our Monte Carlo tool, and also the interaction with our Matlab Schrödinger-Poisson solver. And what does it mean, these setup modules? So we generate objects of device and scenario. And here the device consists of our layer composition, so of our period and of waveguide parameters. But now taking a deeper look into our period, so we have the layers, which consist of well and barrier materials, so indium gallium arsenide and indium aluminum arsenide, and they have specific physical properties. So what do we need? We need the conduction band, or we need the conduction band and edge value, we need the band gap energy, we need the effective masses for the different for our different electron states. So here we also have to take into account effects like non-parabolicity, or if we use a strain compensated design, what effect does the strain have on our conduction band value or on our effective mass. And so we have a quite matured material system to describe our quantum cascade laser. The Ensemble Monte Carlo method, which we use for the carrier transport simulations, is a widely used statistical method for the numerical evaluation of the carrier transport in quantum cascade structures. So our professor is working on this topic for quite a while. So scattering is here self-consistently evaluated based on Fermi's golden rule. All we need are the wave functions calculated with our Schrödinger-Poisson solver, and we take into account all necessary and important scattering mechanisms, such as optical phonons, acoustic phonons, electron-electron scattering, interface roughness, alloy disorder, or impurity scattering. Coming to the second big project in our group, so the mbsolve project, this generalized Maxwell-Bloch framework for the modeling of light-matter interaction in nonlinear optics. Here we are concentrating more or less on quantum cascade lasers. So we provide a universal full-wave semi-classical solver. This is especially important for this DFG simulations, because we have a broad spectrum here extending from terahertz to mid-IR. We provide multi-level simulations, so we can really simulate a full quantum cascade active gain medium laser design, and going beyond the two-level approximation. We provide, or this tool shows numerical efficiency, long-term stability, and and the preservation of the important physical properties. Furthermore, we've implemented some parallelization techniques such as OpenMP and CUDA. And if you're now interested in this tool and you want to use it for your own research, I can provide you the source code, because this is open source available on GitHub. So please feel free to pull it and test it. And if you have questions, please do not hesitate to contact me or group members. And here on the right hand side you see a schematic of the structure of this tool. So this is written in C++. We have again our structure with the device and the scenario, but we also offer a Python interface, so you can specify your simulation setup in a Python script and start it via the Python interface. And it provides a writer, so all specified output values, so all simulation results you're interested in will be written in HDF5 file. So just to give you again a small summary, using an example of a quantum cascade laser. With the Lindblad equations, we simulate the carrier dynamics, so we include the system Hamiltonian, the tunneling between across two periods is described by the tight binding potential, and with the interaction Hamiltonian we describe the optical interaction with the optical field. Then we have Maxwell's equations. And the coupling is described by the quantum mechanical polarization. Coming to our simulation results. So here I investigated a DFG-QCL frequency comp setup published in 2021 based on a dual upper state active region. This is quite important to say, or this is a new developed design where you have two upper states, which provides you with multiple triplets to reinforce or to strengthen your nonlinear mixing process, but also provides broad gain, which is quite necessary here for our terahertz comp simulations or terahertz comp emission. This is based on a strain compensated material system. We have the single mode lasing at 6.5 micron and the comp emission at 6.9 micron, and the experimental measurements show that there's a terahertz comp spectrum extending from 1.8 to 3.3 terahertz. From our EMC calculations, we can extract the absolute value of the second order nonlinear susceptibility, which is around 12 nanometer per volt, for a mixing frequency of 2.5 terahertz. Here the simulation setup which I constructed is schematically described. So we have a DFB grating. On the left hand side we have a high reflection coating, so this is modeled by a perfectly magnetic conductor. Our active region we can describe easily using the coupling constant and the grating period as DFB parameters. The values were given in the experimental paper. And the outcoupling on the right hand side is here modeled using a partially reflecting boundary condition. So we have a relative permeability of this layer, which is based on a perfectly matched layer. So we can introduce impedance mismatch, and we can control this via the relative permeability using the formula on the lower left hand side with our reflectance value. Yes. And what you can see here, we compare the simulation results to the experimental results for the mid-IR spectrum, and this is in good agreement, I would say. Here we are within, this model was at 580 milliamperes, so in between the green and blue spectrum. And here you can see the terahertz frequency comp spectrum. So on the left hand side the simulation results, on the right hand side the experimental results. And as you can see, we also see this broadband this broadband comp emission. And so to summarize, we performed Maxwell-Bloch simulations of a broadband THz DFG-QCL frequency comp approach. We are in really good agreement with the experimental measurements. There is a slight shift towards higher frequencies for the Fabry-Perot comp, which results then in a small redshift in our terahertz frequency comp. So we have a terahertz spectrum extending from 1.4 terahertz to 2.6 terahertz. And to give you a small outlook, what are the next steps? So what I want to do now is I want to integrate a specific dispersion model into our simulations to accurately describe the absorption characteristics for this Cherenkov phase matching scheme. And furthermore, I want to conduct some simulations with different comp setups and also do it for different bias values. So thank you for your attention.